Dear viewers of Akshay.com, by Vetri from Pondicherry. Today, I am going to discuss chemical bonding, another most important chapter in chemistry. Okay, what is chemical bonding? Let me explain with the due time. G.L. Lewis and Kosal in 1916 developed separately theories of chemical bonding. So, G.L. Lewis worked separately and Kosal worked separately in two different laboratories regarding for chemical bonding. And they have proposed a theory, we are calling it as, that is the G.L. Lewis and Kosal theory, we will call it as. So, according to Lewis, he represented symbols or notations to indicate the corresponding valency electrons, what you are seeing here. This is for lithium, beryllium, boron, carbon, nitrogen, oxygen and fluorine. So the dot indicates the valency electron. The interesting information here I want to give, this is purely based on the group it is occupying. A lithium coming under the first group, the valency electron, so indicating one electron, first group 1. Beryllium second group indicating 2. Boron kindly follow indicating 3 electrons. So actually if you look into the long form of periodic table, the boron will come under the 13th group. But actually if you go for the modern periodic table, under this it is coming as 3A. So it is coming into 3A. So the boron corresponding to 3 electrons. The corresponding carbon 4 electrons, valence electrons. Nitrogen 5 electrons. Oxygen 6 electrons. And fluorine 7 electron. And neon 8 electrons. So kindly look at this. I will come back again to discuss. Okay. So what the theory says, that is G.L. Lewis and Kosal theory says, the number of dots around the symbol represents the number of valency electrons. That is the most important information. What will be valency electrons? The electron which will decide the valency, outermost shell. So that number of dots around the symbol represent this number of valency electrons. You have seen already lithium, the corresponding 1 dot, 1 electron. Beryllium 2 electron, like that. So the number of dots around the symbol represent the number of valency electrons. Then next one. The group valency of the elements is generally either equal to number of dots in Lewis symbols or 8 minus the number of dots or valency electron. So this is the most important, the information given by the G.L. Lewis and Kosal. The group valency, that means each group will have a characteristic valency. That's why I informed you earlier, you must have idea regarding for the periodic table. So let me recollect. There are two things I want to remind you to recollect. One is modern periodic table proposed by Moseley, then long form of periodic table. Under the long form, that is the mostly modern periodic table, so we are having 8 groups, and each 8 group, there is up to 7 groups, consists of subgroup A, subgroup B, and 8th group 3, that is group of 3 elements, and 0 group. So these are the imagination. So just recollect that modern periodic table. So group 1, the first group, that is, we'll call it as Roman letter, the corresponding A. In that particular group, hydrogen, lithium, sodium, potassium, rubidium, cesium, francium. All these elements having the outermost shell only 1 electron. So all these symbols, elements, the symbol will be dotted by 1 electron. So this dot or electron will call it as valency electron. Now the idea here it is, so when you move like this, group 1, then second group alkaline earth metals. Then if you go for third A, boron family, third A, carbon 4, nitrogen 5, oxygen 6, halogen 7. Kindly follow. These 7. So these 7. So boron 3 means 3 dots will be there. Carbon again 4 dots. The outermost is 2s2, that is 2p4, 4 the valence electron. When you come for nitrogen, it is 5 dots. But the valency, it is not 5 for nitrogen, it's only 3. So the rule says clearly 8 minus the number of dots for valence electron. So valence electron 5 in the case of nitrogen. So 8 minus 5 means it is 3. So valence of nitrogen family, that is elements, is 3. Go for oxygen. Outermost electron is total is 2s to 2p6. So 2s to 2p4. So 6 electron in the outermost. So 6 means, so 8 minus 6 means 2. The valency of oxygen is 2. Oxygen, sulfur, selenium, tellurium, that is at the particular family. The same we go for halogens. 7 electrons. That is the fluorine, if you take 2s to 2p5. 7 electrons in the outermost. So 8 minus 7, 1. The valency is 1. So this is the interesting information. Kindly listen to me. The group valency. The group valency of the elements. So each element present in the particular group, what is the valence of these elements? That valence will be decided by either by the dot that is present or the 8 minus the dot will give the valency. This is the most important information regarding here. The next one. So the highly electronegative halogens, I have already pointed out halogen family, and highly electropositive alkali metals, this is group 1. So here I want to give again, recollect from my memory. Think of a long form of periodic table. According to long form of periodic table, there are 18 groups. Group 1, alkali metals. Group 2, alkaline earth metal. Then 3 to that is correspondingly to 12, it is the transition elements. Then 13, boron family. 14, carbon family. 15, nitrogen family. 16, oxygen family. 17, halogen family. And 18, zero group elements, inert gas element. So this is according to long form of periodic table. So in this case, when I say the highly electronegative halogen means 17th group. And the highly electropositive alkali metal is first group. So these two are separated by the noble gas element, mean it is 18th group. So 18th group lies between 17th and 1st. So why this is the most important information? Because whenever a chemical bond is formed according to G. N. Lewis and Quasar, they are attaining the nearest stable electronic configuration, either by losing electron, by accepting electron. So that is the most important information. Now you can see the next point. Okay, let me give you some more information. Lewis postulated that atoms achieve the stable octet, octet means 8, stable octet, when they are linked by chemical bonds. Whenever chemical bond is formed, the atom that is involved in chemical bonding will achieve the stable electronic configuration of 8 electrons in the outermost. Okay. In the formation of a molecule or a compound, only the outer shell electrons take part in chemical combination. Kindly follow. This is the interesting information. According to Lewis and Quasar, in the formation of a molecule, only the outer shell electrons take part in a chemical combination, and they are known as valency electrons. So only electron present in the outermost shell only which is involved in chemical bonding. Inner shell they are not involved. So this is the most important information according to Lewis and Quasar theory. The next one. The inner shell's electrons are well protected and they are generally not involved in chemical bonding. So this is according to Lewis and Quasar theory. So in order to understand chemical bonding, the basic idea proposed given by Lewis and Quasar. So according to them, we have to consider only valency electrons. Valency electrons responsible only for chemical bonding, whereas inner shell electrons are well protected, they are not generally involved in the bonding. This is the information just I want to give. Okay, let me come for what is chemical bonding? What are the types of chemical bonding? What is the use? What we can apply for chemical bonding? All these things I will discuss now. So let me enter into the definition. So according to Lewis and Quasar, chemical bonding is defined as a strong force of union of two or more atoms through redistributions of electrons in their valency shells. What way? Either by transfer of electrons from one atom to another, or by process of mutual sharing of electron amongst themselves, so that all the atom acquire the nearest stable noble gas electronic configuration of minimum energy. This is chemical bonding. Let me repeat again. Let me read again. According to Lewis and Kocher theory, chemical bonding is defined as a strong force of union of two or more atoms through the redistributions of electrons in their valence shells, either by transfer of electrons from one atom to another, or by the process of mutual sharing of electrons among themselves, so that all the atoms acquire the nearest noble gas electronic configuration of minimum energy. This is the definition for chemical bonding. Okay, so when you are discussing chemical bonding, what are the types of chemical bonding? So here I have classified into 5 types. Number 1, ionic or electrovalent bond. This is the most important. So ionic or electrovalent bond. This is one of the types of chemical bonding. Number 2, covalent bond. Number 2. Number 3, coordinate covalent bond, or another name, dative bond. That is number 3. 4, metallic bond. Number 4, and hydrogen bond. Number 5. So let me discuss individually, one by one, in detail. You can enjoy. First, let me take now ionic or electrovalent. What is the ionic bond? So let me give you the definition. This is again according to Lewis and Kocher theory. The electrostatic force of attraction operating between the two oppositely charged ions is called ionic bond. The electrostatic force of attractions operating between two oppositely charged ions, positive ion and negative ion, is called ionic bond. Here, the atom that donates electron will be positive. The atom that donates electron will be positive, and the atom that accepts electron will be negative. This is the interesting information. The atom that donates electron will be positive, and the atom that accepts electron will be negative. So there are two ions, positive ion, negative ion, and the electrostatic force operating between these two positive and negative ions, only we are calling it as ionic bonding or electrovalent. Thus, the electrostatic force of attraction operating between these two oppositely charged ions is called ionic bond. This is ionic bond. Okay, this is the definition for ionic. Okay, so when you discuss ionic bond, so let me explain this ionic bond with the two specific examples. There are two examples I am going to discuss here. One is sodium chloride formation ionic bond, and the calcium chloride, another example I am going to discuss to explain how ionic bond is formed. So first let me take now sodium chloride. As you know, sodium occupying the first group and chlorine in 17th group, halogen family. Sodium coming in the alkali metals and chlorine coming under the halogen family, 17th group. Kindly follow me. Now, so what is the electronic configuration of sodium here? Just see here, that is nothing but sodium is 1s2, 2s2, 2p6 and 3s1. This is the electronic configuration of sodium. Just see here, 1s2 here, first level, 1s2. The second level, 2s2, 2p6, 8 electron in this, and third level, only 1 electron in the outermost. So, according to Kocher and Lewis theory, only the electron present in the valence shell will be responsible for bond formation. So, only this 1 electron is going to be involved in the bond formation. Then coming for the other one, the chlorine. I have already pointed out, chlorine is coming under the halogen family. So, the electronic configuration is, again, it is coming in the, I have already pointed out, 17th group. So, electronic configuration is 1s2, 2s2, 2p6 and 3s2, 3p5. So there are 3 levels. So first level 1s2 2 electron here. The second level 2s2 2p6 8 electron in the second level. And third again, so 3s2 3p5. Outermost there are 7 electron. In this case only 1 electron in sodium outermost shell. In the case of chlorine 7 electron in the outermost. So 1, 2, 3, 4, 5, 6, 7 electrons. So what will happen? Now how this is going to form the ionic bond? Let me explain. So sodium I have already pointed out highly electropositive metal. It can donate 1 electron to the chlorine. The chlorine will accept this electron. So according to the theory, the atom that donates electron will be positive. Now it is becoming sodium plus. The atom that accepts electron will be negative. The chlorine, by accepting this electron, becoming negative. And we have discussed in the last class, a positive side, the positive ion will be always smaller than neutral atom. You just compare the size. You can understand. The negative ion will be always larger than neutral atom. Again, you can understand. Okay, let me come for the bonding. Under this, I have already pointed out it is donating 1 electron, chlorine is accepting another electron. So sodium becomes sodium plus and Cl becomes Cl minus. So this extra shell vanishes. The 3s it vanishes, that's why size is becoming smaller. Whereas 1 electron extra, here there is 1, 2, 3, 4, 5, 6, 7 electron in the chlorine. After accepting from sodium, it is becoming 8 electron here in the Cl minus. 8 electron here. So because of this 8 electron, 1 extra electron is not under the control of the protons. So the electronic cloud expands. The size of the Cl minus is greater than neutral atom. So now we are getting a positive ion, we are getting a negative ion. The force of attraction between these two, electrostatic attraction between sodium plus and Cl minus, we are calling it as ionic bond. So one bond is there between. So we can represent simply NaCl, or sometimes we will indicate Na plus Cl minus. It is proved experimentally, even in solid state, it is present in the form of ions. So this is the interesting information regarding for ionic bond formed between sodium chloride. Sodium and chlorine, that is sodium chloride. Okay, let me explain another example. Calcium chloride, formation of calcium chloride, ionic bond. The interesting information is, as usual, calcium is coming in the second group. It is called alkaline earth metal. So beryllium, that is, I can tell you, beryllium, magnesium, calcium, strontium, barium and radium. This is the alkaline earth metals. So automatically calcium coming in the fourth period. Okay. So now just coming for the electronic configuration. There are 4 levels. First one is calcium electronic configuration. First is 1s2. Second is 2s2, 2p6. Then 3s2, 3p6 and 4s2. This is the interesting information. So first level 2 electrons, the second level 8 electrons, third level 8 electrons. So 2 electrons first level, second level 8, third electron 8. The outermost there are 2 electrons. So in calcium there are valence electron is only 2. The outermost shell 2 electron, which is these 2 electrons are going to involve in chemical bonding. This one side. Coming for the other side, that is chlorine. That is, see, this is Cl, this is also Cl, neutral atom. But we have discussed just now, the previous case I have discussed under the sodium chloride. The electronic configuration of chlorine is nothing but it is 1s2, 2s2, 2p6 and 3s2, 3p5. So first case level 2 electrons, it is there. Second case 8 electrons, second level, it is there. And the third level, that is the 7 electron outermost, so in this third level in chlorine. So there are 2 chlorine atoms, in both cases that is 7 plus 7 in this case outer is there. So what is happening? How can we explain the formation of ionic bond under this calcium chloride? So calcium chloride, under the formation of calcium chloride, calcium is donating 1 electron to one chlorine atom, another electron to another chlorine atom. So it is forming 2 bonds, 2 ionic bonds. One is with one chlorine atom, another is with another chlorine atom. So the calcium becomes Ca2+. The interesting information is, if an atom donate 1 electron, it will have 1 positive charge. If 2 electron, it will become 2 positive charge. So in this case, there are 2 chlorine atoms, so automatically Cl minus separately, Cl minus separately, satisfying the total number of positive and negative charges are equal. So, in this case, now the electrostatic force operating between calcium 2 plus positive ion and 2 negative ions, Cl minus and Pl minus, it is called ionic bond. This is the specific example for ionic bond. The same way, we can explain a number of cases, even calcium oxide, we can explain the same way. Okay, let me go with this. I hope these 2 examples will be sufficient to understand what is ionic bond, how ionic bond is formed. Now, next is, what are the characteristic properties of ionic compound? How to recognize a particular compound is ionic or covalent or coordinate covalent, etc. By measuring suitable properties, we can be able to identify. So then I can say, what are the characteristic properties of ionic compound? So here I have listed some 6 properties. Now let me generalize. What is generalization? First one is physical property. Under the physical property, generally we will call it as melting points and boiling point. Solid melting point, liquid boiling points. So what is the characteristic of ionic compound is, generally, ionic compounds will be having high melting and boiling points. They will have very high melting and the very high boiling point because the strong electrostatic force is operating between 2 ions. So to remove these 2 ions, very, very high energy required. That's why it is having high melting and boiling point. We need more energy to separate. So generally, the physical properties like melting points and boiling points will be higher for ionic compounds. That is the first property. The second thing, solubility in water. Because now in this case, generally, all ionic compounds are freely soluble in water. The reason is very simple. So positive ion will be there. So water is an electric dipole. So it will easily, water molecules surround the small positive ion. So it will separate. So more and more water will be easily enter into that. So solubility of water will be very high in the case of ionic compound. Or I can simply say, generally ionic compounds are freely soluble in water. Now, when you are discussing about the solubility in water, automatically we have to discuss about solubility in organic solvent. Organic solvent means what is commonly solvent we are using in the laboratory. Very simple. Alcohol, ethyl alcohol, acetone. So these are the common solvents we are using in laboratory. So it is observed generally, in the case of ionic compound, they are insoluble. Generally, ionic compounds are insoluble in organic solvents. Just opposite to water, solubility of water. The 4th property, existence. The interesting information is, what form this ionic compound will be? Well, they are present in the form of neutral molecules and the form of ions. So what is the way? So very clear is, that is generally, that is always, ionic compound will exist in the form of ion. This is the interesting information. It will exist in the form of ion. In the case of sodium chloride, sodium plus Cl minus. Positive negative ion will be there present. So this is the existence. So automatically, because ions are present, automatically the next property, conductivity. So generally, ionic compounds are good conductors of heat and electricity. Good conductors of heat and electricity. Now, when you come for the plus 2 level, we will be studying electrochemistry. Under the electrochemistry, we will be studying again conductors and insulators. Under the conductors, we are having different types of conductor, and one of the conductors is metallic conductors. That is the electrolytic conductor and the mixed conductor, semiconductor we will be studying there. There, so conductivity may be due to electron, may be due to ion. So this is coming under the ion, the correspondingly ionic conductors. So conductors. So let me generalize. Generally, ionic compounds are good conductors of heat and electricity. Okay. Coming for the reactivity. Because they are present in the form of ions, ion is unstable, so highly reactive. So generally, reactions involving ionic compound will be highly reactive, faster in rate. They will react fastly when compared to organic reaction. Organic reaction molecules are neutral molecules. So all ionic reactivity of ionic compound involved in reaction will be very, very faster. This is the interesting information regarding for properties of ionic compound. Okay, let me go for another video. Now, what are the factors that influence ionic bond? This is another important information. So, what are the factors which influence ionic bond? We are saying, suppose we are saying ionic bond, stronger, weaker, like that we are going to compare. So, which factor will affect this one? So, here I have listed 3 important factors. One is lattice energy is an important factor, will affect the ionic strength. One strength. Ionization energy, we have already discussed under the periodic properties. Electron affinity, again we have discussed already. So these 3 factors which influence ionic bond. Let me give some information how these 3 factors will affect the ionic bond. Now, under this, kindly follow me. The interesting information is, first let me take now lattice energy, then I will go further. So, higher the lattice energy, higher will be ionic strength. This is the one information. Higher the lattice energy, higher will be the ionic strength. This is the first information. So I am giving here lattice energy heading because we are going to concentrate lattice energy, that's why. Now that's the first. So what way the ionic strength will be affected by lattice energy? Higher the lattice energy, I am going to discuss what is lattice energy, how to determine, etc. So higher the lattice energy, higher will be ionic strength. So first factor. The second factor, lower the ionization energy, higher will be the ionic strength. This is another important information. Lower the ionization energy, higher will be the ionic strength. This is the very interesting information. Now let me give a simple example to understand that. Last class, the previous class when I was discussing about the periodic table, periodic properties, I informed ionization energy generally decreases across the group. When you move across the group, it is decreases. So when you take alkali metals, let me start with lithium, sodium, potassium, rubidium, that is, and cesium is going on. Lithium, sodium, potassium, rubidium, cesium, francium. This is the, when you move down, ionization energy, it decreases. Just opposite to the atomic size, decreases. So, now let me take the halogen family, fluorine, chlorine, bromine, iodine, astatine. But generally this fluorine, chlorine, bromine and iodine will form compound with alkali metal. This is generally ionic compound. This is the interesting information. Generally a strong ionic compound will form always between alkali metals and the halogen family. Here I want to give one information. That is, kindly follow, lower the ionization energy. That means when you move down, ionization decreases. Higher will be the ionic strength. So ionic bond strength will increase. So let me take chlorine now. So compare lithium chloride, sodium chloride, potassium chloride, and you can think of rubidium chloride. So like that. So what is the idea here? You compare lithium chloride and compare sodium chloride. Let me take these two. You compare lithium chloride, compare sodium chloride. So according to this, sodium will have low ionization energy, so ionic strength will be so. That means sodium chloride will be more ionic than lithium chloride. This is the interesting information I want to give. Comparison. Or potassium chloride will be more ionic than sodium. Like that, we can compare. So, if you know the position of the elements, the alkali as well as the halogen family members, we can approximately compare which is higher in ionic strength, etc. So that second part, so lower the ionization energy, higher will be ionic strength. So the interesting information I have explained. The same way. Next one. Higher the electron affinity, higher will be the ionic strength. This is another interesting periodic property. It is affecting the what you can call ionic bond. So higher the electron affinity. Again you go for the electron affinity in the case of fluorine, chlorine, bromine, iodine. And I have already discussed on the periodic properties. Affinity. The normal expected order is electron affinity. When you move down across the group, it should be decreases. This is the normal order. Normally electron affinity decreases across the group, specifically fluorine, chlorine, bromine, iodine. But exceptionally, chlorine is having higher electron affinity than even fluorine. I have a reason I have already explained the last class. That is due to size. So in this case, order will be here. Chlorine will be more electron affinity than fluorine, which is more electron affinity than bromine and then iodine. This is the normal order. Suppose let me take chlorine alone. And you connect with another thing, that is higher the electron affinity will be the ionic strength in the sense. Now you take in this case metal. So I can compare now sodium fluoride, that is sodium chloride, sodium bromide and sodium iodide like that, and sodium fluoride like that. So what I can compare the ionic strength both cases. Now what will happen, the left side is metal is common, the right side affinity that is increases. So chlorine is more high electron affinity than fluorine, bromine, iodine, etc. So automatically higher electron affinity, higher will be ionic strength. So sodium chloride will be higher ionic strength. We can compare, we can give the information from this. So this is the most important information. So if you understand this basic idea, any commodity question we can easily answer. Okay, let me go for the next. Lattice energy. So I have discussed, because the electron ionization energy and electron affinity I have discussed. Only lattice energy, the new term it is. So now I am going to discuss this lattice energy. What is lattice energy? The energy released when one mole crystal of solid is formed from the constituent gaseous ion separated from each other by infinite distances. This is called lattice energy. So there are ions, positive ion and negative ion. So let us assume sodium plus ion, Cl minus in gaseous form, it is different, infinite distance. And when you are bringing these two ions to form a 1 mole crystal of a solid, whatever energy released, we are calling it as lattice energy. Let me repeat again. The energy released when 1 mole crystal of solid is formed from the constituent gaseous ions separated from each other by infinite distances, then we will call it as lattice energy. In other way also I can define. What the other way? The other way definition is the energy required to separate completely 1 mole of a solid ionic compound into its gaseous constituent ions. So this is again called lattice energy. So lattice energy I can define in two ways. I can define in terms of energy released, or I can define in terms of energy required. So let me, second statement, let me again repeat. The energy required to separate completely 1 mole of a solid ionic compound into its constituent ion, gaseous constituent ion, that is called lattice energy. Now that ion is called, we will call it as, that is lattice energy. This is lattice energy. Example, let me give an example, sodium chloride. So sodium chloride, it is experimentally given value, it is observed value, it is plus 788 kilojoule per mole. A very high lattice energy, because you know already we have just now I have discussed, the ionic strength is very high. So this is the experimental value, plus 788 kilojoule per mole. This is the lattice energy. Okay, let me explain. Now, so what are the factors that affect lattice energy? Previously I discussed what are the factors which affect the ionic strength, ionic bond. Now I am coming for this lattice energy. What are the factors which will affect lattice energy? Now, I can give one by one. That is, number 1, higher the charge and smaller the radii, higher will be the lattice energy. This is first information. Higher the charge and smaller the radii, higher will be lattice energy. So lattice energy will be higher whenever ions having higher charges, plus 2, plus 3, plus 4, like that you can. Higher the charges and smaller the radii. Radius should be very, very smaller. Then higher will be the lattice energy. This is one point. Then second, more stable the ionic compound, higher will be the lattice energy. There is another interesting information. So compound is more stable, ionic compound is more stable, then corresponding that higher will be the lattice energy. So lattice energy depends on ionic strength. Then solubility also. Lower the solubility, higher will be the lattice energy. So it depends on solubility. From the solubility we can affect, that is solubility will affect the lattice energy. So these are the factors which affect lattice energy. Okay. Now, how to determine this lattice energy? Let me explain this. Here, I am introducing a cycle called Bonhoeffer cycle. Normally, in board examination, they will ask write notes on Bonhoeffer cycle. Okay, let me explain here. What is Bonhoeffer cycle? With the help of Bonhoeffer cycle, how to determine the lattice energy, I will explain here. Okay, so basic idea here it is. 1 mole of solid sodium reacts with, that is, half mole of chlorine gas react to produce 1 mole of sodium chloride solid. This is the reaction. So if you are allowed to react 1 mole of solid sodium and half a mole of chlorine, that is gaseous chlorine, to react to produce, then 1 mole of sodium chloride will produce. That we will call it as heat of formation of 1 mole of sodium chloride. So this is the equation. This we can delta H of heat of formation we can determine experimentally. There are methods. Okay. Now our aim is how to determine the lattice energy. So let me explain the cycle now. So here I am going to consider sodium solid separately, chlorine gas separately. Then how from this, that we have already discussed lattice energy. That is, two ways I have discussed lattice energy. One is, there are two ions for the infinite distance. We will bring together to form a 1 mole of sodium chloride system. That is called lattice energy. The other way, we have sodium chloride 1 mole solid, we will break into 2 the infinite distance to move away the sodium plus sodium, and that is also lattice energy. Here, I am going to use here, I will keep 2 different ions, sodium plus and Cl minus in the infinite distances. I am bringing and forming 1 mole of solid, whatever energy released, that I am going to call it as lattice energy. So let me take first one, sodium, 1 mole of sodium solid. So 1 mole of sodium solid, now I will convert into sodium gas. What way? That we will call it as heat of sublimation. The term I am using here, delta H1 dot. Delta H1 dot is the heat of energy required to convert 1 mole of solid to 1 mole of sodium gas. Solid sodium will be converted into the sodium gas. Whatever energy required, we call it the heat of sublimation. It is indicated by delta H1 dot. Then after converting sodium gas, a sodium gas will be converted into sodium ion, that is called ionization energy. I have already explained under the periodic property. That is indicated by delta H3 dot. Ionization energy, it is the energy required to remove 1 electron from the outermost shell. That is ionization energy. So that is there. So we are getting now sodium plus. So we are getting the sodium plus in gaseous state. So sodium solid converted into sodium gas. Sodium gas is getting converted into sodium ion in gas. That we are having in the left side. Thus again we take now chlorine gas of mole gaseous. Now this chlorine gas will dissociate to form chlorine atom in gaseous state. That is called heat of dissociation. The heat of dissociation indicated by delta H2 dot. This is the heat of dissociation in terms of energy. Then after the conversion of chlorine gas, atom, atomic chlorine gas, now we will again ionize. What way? It will be converting by accepting 1 electron, chlorine will become chlorine negative. So that energy is called electron affinity. We have already discussed. What is electron affinity? It is the energy released when 1 electron is added to the outermost shell of a neutral gaseous atom. So here neutral gas is the atom chlorine. When 1 electron is added, chlorine minus is formed. Whatever energy required, we will call it as electron. The energy released, we are calling it as electron affinity. So we are having sodium plus, we are having sodium, the Cl minus in both in gaseous form. Now we are getting the terms now, delta H1 heat of sublimation, delta H2 here in the case of chlorine heat of dissociation, delta H3 ionization in the case of sodium, and electron affinity in the case of chlorine. So we are getting sodium plus ion and sodium minus, the Cl minus ion, and these two ions combine to form 1 mole of sodium chloride solid. That term I am introducing as delta H5 dot. It is nothing but lattice energy. So lattice energy, so that is 1 mole of sodium chloride solid is formed from 1 mole of sodium ion in gaseous state, 1 mole of sodium, that is 1 mole of chlorine ion in gaseous form to form 1 mole of sodium chloride crystal. That is represented by that whatever energy released, we will call it the delta H5 dot. It is lattice energy. Now this is called Bonhoeffer cycle. So connecting all these terms, I can give an equation form. Just see that equation. This is the equation. That is we are getting the help of Hess law that we will be studying under the thermodynamics. Hess law. That is delta H of heat of formation of 1 mole of sodium chloride crystal, that is equal to delta H1, delta H2, delta H3, delta H4 and delta H5. Can you follow? All the terms that is involved in the Bonaparte cycle, that is nothing but delta H4. So here what are the terms we can determine experimentally? Delta H of we can measure in the equation, that is the reactions. Delta H1 we can measure, delta H2 we can measure, delta H3 we can measure, delta H4 we can measure experimentally. Only delta H5, that is lattice energy, we cannot measure. So that we can determine with the help of Bonaparte cycle. What way? So I will rewrite the equation. So my aim is I want to get delta H5. What is delta H5 then? I will rewrite. So automatically delta H minus of all the terms, it is given clear. So delta H of minus, it is square bracket, delta H1, delta H2, delta H3 and delta H4. These terms, if you subtract all these values from the delta H of, you will get the value of delta H5. That is nothing but lattice energy. So lattice energy, thus we can calculate with the help of Bonaparte cycle. This is the most interesting information. Can you follow? Problem will be asked based on this one. So can you see this is the Bonaparte cycle? So from this, now we are determining this value delta H5 lattice energy we are determining, because this is experimentally determined and this is experimentally determined, this is experimentally determined, this is experimentally determined. So by subtracting all the values, that is these 4 values, from this we'll get this value. That is the equation I have shown here. So thus the lattice energy can be calculated. This is the interesting information. Okay. Let me give one more information under the ionic bond. Whenever you say ionic bond means 100% it will not be ionic. Suppose you take HF, HCl, HBr, HI, they are different compounds. And if you compare the ionic bond, ionic strength in this, all the cases 100% will be, one will be higher, another will be lower like this. So how to compare this strength? So when you are comparing the ionic strength and this different compound, the next question arises, what is there is some partial covalent character in the ionic compound, ionic bond. So that I am going to discuss here. That is partial covalent character of ionic bond that can be explained with the help of Fajon's rule. Kindly follow. This is the most important information. And a number of competitive questions will be asked under this using this Fajon's rule. So kindly listen me. I will explain slowly. You can understand. In majority IIT questions are based on the Fajon's rule. Okay. Now let me explain. An ionic compound tends to have appreciable covalent character. I have already explained ionic character, but I have not explained covalent character. We are going to discuss anyhow. So here, which can be explained by Fajon's rules. Then you can ask, what is Fajon's rule? I will explain now. According to Fajon's rule, this is I am going to discuss now. According to Fajon's rule, high charge and the cation or anion or both will favor covalent character. This is the interesting information. High charge on the cation or anion or both will favor covalent character. So this is the interesting fact. Suppose you compare now sodium chloride. We have discussed already, it's a very ionic compound. Even in solid state, it is present in the form of ion. The most ionic compound. Suppose you compare with calcium chloride. The interesting information. I am keeping chlorine common, but metal I am changing. Positive ion I am changing. You compare the ionic state. So the Fajon's rule gives a very clear idea. Which is more ionic? This will give answer. Because higher charge than the cation. So in sodium 1 plus, in calcium 2 plus. Kindly follow. So calcium 2 plus, sodium 1 plus. The Fajon's rule says higher charge than the cation. So here anion is common, there is no problem. higher charge than the cation will favor covalent character. So when you compare sodium chloride, calcium chloride is less ionic. A slightly more, that is, a covalent character is there in calcium chloride. So I can simply say sodium chloride is more ionic than calcium chloride. I can compare very easily. So whenever any question is asked, one among the following is more ionic, one among the following is more covalent, Pajan's rules is very, very useful to compare. Kindly have it in mind. So in this specific example I have given, so calcium chloride, sodium chloride, when you compare, sodium chloride is more ionic than calcium chloride because according to Pajan's rule. Pajan's rule says higher charge than the cation, so will favor covalent character, so less ionic in the case of calcium chloride. That's the first point. The next one, smaller size of the cation will favor covalent character. So cationic size will favor covalent character. That is the most important. Okay, let me take again. And let me give now. Lithium chloride, sodium chloride, potassium chloride, like that will go now. So right side, because I am concentrating on cation. So I am keeping in three cases, chlorine is I am keeping common, so that anion part is not coming in this here. So when you compare left side, lithium plus, sodium plus and potassium plus, again unipositive. So charge also it is not playing any difference there. The only difference is here size. So kindly follow. Smaller size of the cation will favor covalent character. So according to the question is, which is more ionic, which is more covalent? So among this we know already, they are in the alkali metals, except hydrogen which is a gas, lithium, sodium, potassium, rubidium, cesium and francium. So when you move across the group, size increases, I have discussed. Size increases, I have discussed. When size increases means automatically potassium will be greater than sodium, sodium will be greater than lithium in this case. So smaller size is lithium. So here smaller the size of the cation will favor covalent character. So lithium chloride is more towards covalent when compared to sodium chloride, when compared to potassium chloride. So less ionic, lithium chloride is less ionic or more towards covalent character. So that we can compare with the second rule of Pajan. So smaller size of the cation will favor covalent character. This is the very interesting information we are getting from this Pajan's rule. Okay, let me go for the next rule. Large size of the anion will favor covalent character. Large size of the anion will favor covalent character. I can now take a specific example, large size of the anion. So what I will do now, I will keep the cation common. Sodium fluoride, sodium chloride, sodium bromide and sodium iodide, like this we can. So for the, if you want, I will do one thing, this because affinity anomaly will be there, so better I will remove this sodium chloride. Let me compare now. Sodium chloride, sodium chloride, sodium bromide and sodium iodide I want to compare. I want to compare this. What way? Now let me explain the third Pajan's rule is this. Larger size of the anion. So when you move down, chlorine, bromine, iodine, the size of the anion is increasing. The iodine is more atomic size than bromine. Bromine is more atomic size than chlorine. The size of the bromine is greater than chlorine. So larger size of the anion will favor covalent character. According to this, sodium iodide is more covalent, whereas sodium chloride is more ionic. I can now compare the ionic character of a compound with the help of the third rule. So kindly follow. This is a very, very interesting information I want to give. So charge, number rule, according to Pajan's rule, there are three rules. Higher charge on the cation anion will favor covalent character. So lower the charge, higher will be ionic. The smaller size of the cation will favor covalent character. So automatically the larger cation will favor the ionic. Automatically here in this case, larger size of the anion will favor covalent character. Then automatically smaller size of the anion will favor the ionic character. This is the interesting important compound. So let me go for the next one. So based on the Pajan's rule, we can very easily compare which is more ionic, which is more covalent, like that we can compare. Okay, let me go for the next one. So that is regarding for ionic bond. So I now explain what is ionic, what are the factors which influence ionic. Under this I have discussed lattice energy, and also partial covalent current and ion state. Okay, with this, let me go for the next bond, covalent bond. What is covalent bond? The definition is, according to again Lewis and Coastal theory, a covalent bond is formed by mutual sharing of electrons between two atoms from their valency shell to complete their respective object. A covalent bond is formed by mutual sharing of electron between two atoms from their valence shell to complete their respective object. To attain stable electronic configuration of 8 electrons in the outermost, they are sharing between. So this is called covalent bond. Okay. So a specific example, one example, I am giving here hydrogen. Electronic configuration is 1s1, 1. Here is again 1s1, 2 hydrogen atoms. Outermost electron is 1 electron, hydrogen, another electron. So when you are keeping here, this is the nucleus center. So 1 electron. So this is 1 electron, this is another electron. So when they are coming in between, the mutually shared. So hydrogen bond is formed. So when it is forming hydrogen bond, the nearest is helium. Stable electronic configuration. So here kindly give, I want to give one information. Even the rule says octet theory, 8 electrons. So formation of hydrogen molecule in exceptional case, it is resembling helium where there is no 8 electron, only 2 electrons. This you have to keep it in mind. But if you go for chlorine, if you go for bromine or any other diatomic molecule, always it satisfies the 8 electrons in the octet. When I will be discussing in future regarding to the different theories to explain the covalent bond, I will give more examples there. Okay, before that, let me explain what are the characteristic properties of covalent compound. I have already discussed under the ionic what are the characteristics. Now here I will discuss what are the characteristic properties of covalent compound. Now as usual, physical properties mean I will take melting points and boiling points. Melting point for solid and boiling point for liquids. So generally, covalent compounds will be having lower melting and boiling point and compared to ionic. Lower melting and boiling points, because here molecules are neutral. They are in molecule, there is no ions. So we will be discussing later. So generally, low melting and low boiling points. Now, coming for solubility, that is generally covalent compounds are insoluble in water. Generally insoluble, just the reverse of ionic. Third property, generally covalent compounds are soluble in organic solvent. It is soluble in organic solvent. Then coming for the existence, occurrence. Generally, I have already just now I have pointed out, covalent compounds are always present in the form of molecules, neutral molecules. There is no ions. Neutral molecule, H2 molecule, bond is covalent. Cl2 molecule. So it is a molecule. So methane molecule. So it is present in the form of molecule. There is no ion present. So existence is a molecular form. Since they are present in the form of molecular form, the conductivity very, very low. That means generally covalent compounds will have lower conductivity. It's the poor conductors of heat and electricity. Now, coming for the reactivity. Generally reactions involving covalent compounds are low reactive. It is very, very, very less. Speed will be less. Because the involved species or molecules generally will react slow and compared to ionic, which are faster. So, generally, covalent compounds will be lower melting and boiling points. Generally, it is insoluble in water, whereas soluble in organic solvents. They will generally, covalent compounds are present in the form of molecules. Regarding for conductivity, generally, covalent compounds are poor conductor of heat and electricity. And finally, coming for the reactivity, generally less reactive. Covalent compound reactions involving covalent compound generally low speed, that is low reactivity. This is the interesting information regarding the properties. Now, let me go in detail. The theories which will explain what is covalent bond and what are the characteristic properties of covalent bond. In order to explain, different theories were proposed. I will go each theory in detail to explain, to understand covalent bond. So let me hear. To understand covalent bond in detail, it is necessary to understand the following theories and concepts. This is the most important. So a number of theories proposed to explain the covalent bond. So all these theories very, very essential because a number of questions are asked in IIT, JIPMA and NEET based on this covalent bond. The first theory, Lewis theory or Ogden rule, Ogden theory. I have already indicated under the ionic bond. So I will go in detail of Lewis theory. That's the first theory. Lewis proposed. The next one, Sidwick bound theory proposed in 1940 to explain the shape of molecules, covalent molecules. The third theory, valency shell electron pair repulsion theory. This is the most important. Valency shell electron pair repulsion theory. Another interesting information. So we can predict any shape of any molecule with the help of correctly, even angled, with the help of valency electron pair repulsion theory. The next one, valence bond theory. We will speak in terms of orbital. We can have a very clear idea how a covalent bond is formed, how many bonds or covalent bonds are formed. All this information we can get from the valence bond theory. The next one, hybridization concept. This is an anomaly. This is very interesting information because a number of cases, let's say for example, divalence of boron, trivalence, the divalence of beryllium, trivalence of boron, tetravalence of carbon, we cannot explain by the valence bond theory, but hybridization concept gives very clear idea. So we must understand what is hybridization concept. Then another interesting information, molecular orbital theory also, it is very necessary we must understand to understand the covalent bond. Because molecular orbital theory gives information, this is the magnetic character, paramagnetic character, bond order, bond stability, everything this molecular orbital theory gives information. Okay, let me go one by one, each theory, so kindly follow me. Let me first take Lewis theory or Ogden rule. What do the theory says? When two atoms combine to form a covalent bond by mutual sharing, I have already explained the case of hydrogen, mutual sharing, they attain an inert gas configuration with an octet of electron, with 8 electrons. This is the most important information. So during the formation of hydrogen bond, hydrogen bond between hydrogen molecule, I have explained it's an exceptional case where only 2 electrons. But in this case, except that hydrogen, all the remaining, always 8 electrons in the outermost. You take now fluorine, chlorine, bromine, iodine, and always they are by mutual sharing, they are attaining 8 electrons in the outermost. I will be explaining. So, but anyhow, a number of cases, there is anomaly we are observing, there is deviation. There are a number of examples, molecules, this rule is not followed, Ogden rule is not followed. So let me explain that. That we will call it a deviation. So deviation I can classify into 2 ways, namely, that is less than Ogden, less than 8 electron, hydrogen is a specific example, less than 8 electron. So here a specific example given, boron trichloride, nitric oxide is less than Ogden. But more than Ogden, specific example, phosphorus, pentachloride, ClF3, ICl3, these are specific examples. Okay, so normally whenever 2 atoms combine to form a covalent bond by mutual sharing, they attain inert gas configuration with the octet of 8 electrons. But in a number of cases there is deviation. Deviation can be classified in 2 ways. One is less than Ogden and more than Ogden. So let me explain this one. That is, before going for the Sidwick bound theory, let me explain this. So I will first explain what is less than Ogden. Let me take boron trichloride. Let me take boron trichloride. I will explain. Under the boron trichloride, boron electronic configuration is, I can now write 1s2, 2s2, 2p1. This is the electronic configuration of boron. Coming for chlorine, again electronic configuration is, that is 1s2, 2s2, 2p6, and 3s2, 3p5. This is the electronic configuration of chlorine. So, the outermost shell 7 electrons in chlorine, outermost shell in boron 3 electrons. So, I can now, according to Lewis concept, so boron I can write here, that is boron 3 dot indicating 3 electrons, valence electrons. Whereas coming for the chlorine, chlorine is having again outermost electrons, that is 3, that is 5 plus 2, 7 electrons. So how we can explain that? Now let me draw now, kindly follow. Now let me take this. That is boron center, 1 electron here, 1 electron here and 1 electron. So coming for the chlorine, I have already pointed out, there are 7 electrons in the outer shell. So 2 here, 2 here and 2 here. One more is here. The same way here, coming for the chlorine, 2 here, 2 here, 2 here. So this is again another chlorine atom, 2 here, 2 here and 2 here. So there is one more. So now if you take this chlorine alone, if you count outermost, that is 8 electrons. This chlorine, if you count, you just see 8 electrons, and this chlorine, if you see 8 electrons. But if you go for boron alone, it is only 6 electron, 8 electron is not there. So it is less than or there. Normally this boron trichloride, this type of molecule will be unstable. They will always move towards a pair of electrons. So they will usually form coordinate covalent bond. I will be discussing later. This is the interesting thing. So this is a specific example. It is the octet rule is failed. Less than 8 electron. One example. So another interesting is, I will explain PCl5. It is more than octet. Let me take now phosphorus. So phosphorus electronic configuration coming under the nitrogen family. Again 5 electrons in the outermost. So 1 here, 2, 3, 4, 5 electrons. Outermost. It is nothing but 3s2 that is corresponding to 3s2 3p3. That is the electronic outermost shell. So 5 electrons. So coming for the chlorine, as you know, 7 electrons. So here chlorine 2, 2. Here is also 2. This is the electron. The same way here chlorine. This is chlorine. So 1 electron here Cl. 2 here, 2 here, 2 here, 2 here. Here again 2 electrons. The same way here chlorine. 2 here, 2 here, 2 here. So again this 1 electron here. In this case totally 3. So 1 electron here. Now 1, 2, 3. Then again in this case there is 1, 2, 3. Then one more here. In this case chlorine again 2 electrons here. 2 here, 2 here, 2 here, 2 here, 2 again. Though here there is one more electron here. Then again one more 2, 2, 2, 2. Here again 2. So 1 electron here. So the interesting information here, these two, the chlorine here, by taking 1 electron from the phosphorus, that is again 8 electrons, and again same way here 8 electrons, and again here 8 electrons, and again here 8 electrons, and again here including this 8 electrons. But if you consider in the center, that is 2 here, it will be 10 electrons. Surrounding the phosphorus 10 electrons. It is not obeying. So chlorine is only 8 electron outermost configuration completing octet. Here again chlorine 8 electron, here chlorine 8 electron, here chlorine 8 electron, here chlorine 8 electron. But central phosphorus is not obeying, because if you take that is 5 electron in the phosphorus, 5 electron from 5 chlorine atom mutually sharing, so totally 10 electron, 10 electron. So phosphorus is not obeying. That means it is violating the octet rule. More than octet, more than 8 electron. This is the specific example of the corresponding the Lewis theory fails. So this is the interesting informations I can give. So I hope I can explain. The remaining next class I can explain. Okay, thank you.